Hello students, today we will go to the fourth lecture in this series that we are looking at modern world architecture, and we last time saw the age of the intellectual revolution and we focused on the 18th century developments. We talked about the rise of neoclassical architecture and how neoclassicism had four stages. It evolved from being a rational movement, that is very much borrowing from classical architecture, evolving to archaeological neoclassicism, radical and then visionary neoclassicism with the works of Bully and Ledoux, and how tremendous change came, at least in the way they were perceiving form, that it has to be unornamented, it has to be rational, and they were borrowing from classical principles of symmetry, and in the end we saw pure geometry. So what we find is that in the 18th century the foundations of modern architecture were being laid. If 18th century was the age of the intellectual revolution, the 19th century is the age of the industrial revolution. And today in this 21st century, the kind of industrialized world we are living in is because of this tremendous revolution that happened in the 19th century. There was breakneck development in technology and ushered in an industrial society. From handmade production that used to happen in guilds, you might have studied about that in school. From handmade production we went to factory production through machines, and mechanized factory system replaced these home workshops. We were able to produce vastly improved goods both in quality and in quantity. Water power and steam power came, and that also led to the production of iron of much better quality and the development of machine tools, which we know have made a major difference. Now if we look at industrial revolution overall, there have been four stages and currently we are in the fourth stage. The stage number 1 is when mechanization and steam power came. Stage number 2 is from 1870 when assembly line mass production began. The most famous example is that of the Ford motor car in the beginning of the 20th century. And then in 1969 we ushered in automation and electronics, and a completely new era of electronics began. Today in 2024, starting from around 2010-2011, we have cyber physical systems, networks, digitization. Today we have AI and machine learning, and we are moving into a completely new world. All this began in the 19th century or end of 18th century with the rise of the Industrial Revolution. Now just to give you an example of how Industrial Revolution has impacted development or impacted machines, including cars, etc., is the case of the Mercedes-Benz. If you look at the Mercedes-Benz, the earliest model in 1886, and if you look at it today in 2018-2024, the car has undergone a massive change, and the cars we drive today are so different from the one that began, but the foundation was laid in the Industrial Revolution. So because of this, many technological and architectural innovations happened, with Britain being in the forefront. Now one of the strongest developments, or rather the power behind the Industrial Revolution, turned out to be the steam engine that appeared in railway transportation, a most important technological development or invention of the 19th century and a key component of Industrial Revolution. James Watt, as you might have studied in history, was the one who discovered the power of steam and brought in the steam engine in 1785. George Stephenson further improved it with the first passenger locomotive in 1825. Darby produced pig iron in the blast furnace using coke rather than charcoal, which allowed for large scale production. It was a better ingredient for the production of iron, and this process that he invented was a major step in producing iron as a raw material in large quantities needed in the Industrial Revolution. Rotary steam power and iron frame both happened at the same time. Now because of the coming in of iron in such a major way, they started exploring its uses in various ways. For example, Wilkinson, Darby and Thomas Pritchard was an architect. they designed or and implemented the first iron bridge in the world, first cast iron bridge in those, it was just cast iron in those days. It is in Colebrookdale and it's just about 30 meters long. Now keep this in mind when we look at much larger bridges in this presentation. Because of the way iron was coming in, though I have written here application of steel because this steel is what we use today, but it was predominantly cast iron that was being used at the time in buildings, in bridges and in railway lines. These cast iron columns then began to replace wooden columns in factories or in the cotton mills of England. Very important because wood was more prone to destruction and fire, whereas fireproofed iron columns are much more stronger, more durable and overall strength was much higher. As you can see here, and this change of skylight bringing light from the top, we will see it later, and how because of iron and then glass major changes came. The invention of the steam engine also led to the powering of factories which were producing goods in mass quantities. There was a major growth in textile mills. Factories required coal, coal had to be mined and that coal had to be transported and that was to the factories and that was done through the railways. These are the earliest railway engines that we see of that period, and how the stations have evolved. These are beautiful two stations of the late 19th, early 20th century. This is the Kazansky railway station in Moscow in 1940 and the Grand Central in New York in 1919. Very, very ornamental, decorative, neoclassical ideas are also there. And then we find today's stations which are very much evolved using more of steel and glass, etc. The Kanazawa station in Japan in 2005 and the Oriente station by Santiago Calatrava in Portugal in 1998. Now the first iron frame building was a 28,000 square feet flax mill which was built by John Marshall. He wanted a fire resistant building because he was producing textiles and he commissioned architect Charles Babbage to make a fire resistant building, and thus the concept of a metal framed fireproofed member or fire resistant member building was born. Now cast iron is brittle and poor in tension as compared to the steel that we use today. It does not have the same advantages, but this building is a beginner. This building in 1796 is a beginner towards a steel framed skyscrapers, though it had got external walls and it had got these walls in brickwork. But as you can see how the skyscrapers have evolved, and we will see more of that when we look at Chicago where the tall office building came up, and this development by John Marshall's factory was a vital step towards the skyscrapers that finally came up in Chicago because of iron framed construction. So we find this Reliance building in 1894 evolving into a fully steel framed moment frame skyscraper by a Seagram building by Mies van der Rohe, and then we have how tremendously skyscrapers or tall buildings have evolved with the Burj Khalifa, the tallest in the world, in 2004. New materials started playing an important role. We already seen that cast iron came in, but steel was invented through the Bessemer process, and it was Henry Bessemer who patented it in 1856. Steel began to be produced in mass quantities. It was more economical now being produced in such a large quantity. Both quality and quantity were improving, strong and durable than masonry, and much more slender members were possible. Now tremendously steel production grew. You can look at this graph. If steel production in the beginning of the 19th century was somewhere less than a million tons, went up to 40 million tons, 40 million tons, just about 800,000 tons to 40 million tons by the end of the 19th century. And this is very important because steel has played such a tremendous role in modern architecture. Another important, very important material, probably in some ways more important than steel, is the invention of Portland cement by William Aspen and patented in 1824. Another material that has played was going to play a more important role in modern architecture is glass. Glass was there earlier, but not the kind of very transparent and straight glass that was now invented in the late 18th century. Large glass panes were produced. 1845, the modern glass industry for window glass came up, leading to what we use today is float glass, completely transparent glass that gives a very clear view as you look outside. And then laminated glass for larger glass panes came up in 1903. Now, with these new materials and in engineering, one major change that happened was structural design. It was clearly understood before the 19th century, structural forces were understood empirically, hit and trial method. But now in the 19th century, exact science began to be used. Buildings were being structurally designed, made in RCC, which we'll talk about, or in steel and glass, and there were exact knowledge of law of statics was needed, and structural calculations were essential for iron frame construction. As a result of this, a completely new profession came up. Now, military engineers were already there. They were a part of helping nations in warfare, in building bridges, for example, or other structures that were needed during war. These military engineers then began to be trained to become civil engineers for public buildings or for normal buildings needed by the society. And because of this, the entire built environment professionals got divided into two for the first time, architects and civil engineers. And by the mid and late 19th century, we find there was spectacular advances made by civil engineers, and I'll tell you the reason why. Now, this is how iron bridges came up in the 19th century. And you can see from Colebrookdale that I showed you earlier to much larger spans that started being built. Now, one of the longest spans that was built during this time was the Brooklyn Bridge connecting Brooklyn with Manhattan, and this bridge was designed, executed by John Augustus Roebling, 1869-1883, with a total span of close to 500 meters, magnificent work in exposed iron engineering. And one of the reasons why they were able to do it, and I'll talk about it later, is that they had no historical baggage. They did not carry ideas of bringing in classical architecture, etc., etc. It was more or less a pure engineering feat. There were some architectural features. For example, this pier that you see, one on this side and the one on the other side of the river, is something called, we can call it an Egyptian Roman Gothic combination. If you look at the pier, the overall pier has the idea of a pylon, but if you look at the cutouts that have been made, reminds you of Gothic architecture, and the pier overall is also resembling a Roman triumphal arch. So, it is an Egypto-Gothic Roman pier. That is the only, what you could call the semblance of an architectural intervention that you find here. Essentially, it is an engineering marvel of the time, with 4 supporting cables supporting the bridge. Diameter each cable is 15.5 inches, more than 11,000 tons of cable strength was there. The weight of each, the ultimate strength of the cable, and the weight of each cable was close to 3,500 tons. Now, two kinds of bridges is what we see in our times. One is the suspension bridge, and then is the cable stayed. What is the difference between the two? A suspension bridge is one where you have these piers and you have cables which are running over the piers, but they are basically held by very strong foundations on both sides of the water body. So, the cables are not, the weight is not being transferred anywhere but directly here, and then the cable is transferring the weight on the other side. A cable stayed bridge, on the other hand, the piers become very important. These cables are running from the pier and they are holding the bridge like this, they are pulling the bridge like this. These cables are staying the bridge and the load is being transferred to this column down into the foundation. So that's the what you would call the simple difference between a suspension and a cable stayed bridge. This is an example. This is the Golden Gate Bridge, which is, as you can see, a suspension bridge, and this is a bridge of our modern times. This is a cable stayed bridge where the cables are holding or staying the bridge by transferring the load to the piers on both sides. Now, another bridge that was built later, and John Roebling's Sun Company built that bridge later, was in the 20th century, is the Golden Gate Bridge in San Francisco. This bridge is a further extension of what he had done, John Roebling had done earlier in the Brooklyn Bridge. Now, it has only two main cables. So therefore, if you compare Brooklyn with Golden Gate, reason why I am doing that is to show you how quickly engineering advances took place, where in the earlier bridge it was only about 500, this was about 2700 meters. Yeah, it was nearly 5.5 times longer. Brooklyn had 4 main cables, this had only 2 main cables. It was carrying about 13,000 tons of weight, whereas these 2 main cables were carrying about 24,500 tons. So that is one thing that happened. And the other thing, that I can show you here is that in this Brooklyn Bridge, if you just look at the cables, and they have kept a cable symbolically there to show you what is inside each cable. Each cable, there are 2 main cables with 61 bundles of 452 wires each. There are 61 bundles of 452 wires each that are all put together in each cable. So, one and then the other cable. Another major advance that took place, which has played a very important role in 20th century architecture and even today, is the coming in of the ice section, the steel ice section. There was a continual effort to improve the spanning capacity which we had of iron beams and rails, and in the early decades of the 19th century, railway tracks evolved later on to standard structural I-beams, right. These are the earlier versions, and later on we see, when we look at the works of architects like Mies van der Rohe, ice sections, the final ice sections began to be used. Now, an all iron skeleton frame building is also the Minier chocolate factory. It's there even today. It's a heritage building, and the first building in complete iron skeleton, infilled with these colored enamel bricks on the outside, giving a very wonderful ornamentation on the outer facade. And it also used cross bracing. I am sorry that the pictures are not able to show you very clearly, but if you can look at it here, there are these cross bracings running, and this was very important for architecture, modern technology in architecture. Now, Francois Coyne was the one who brought in the first real use of reinforced cement concrete, and he built the first RCC structure, which was the house that he built using RCC. Then major development took place under Francois Hennebick. So from 1870 to 1900, we find an intense development in RCC work happening in Germany, America, England and France. In 1892, Francois Hennebick, a French engineer, developed monolithic construction. That is, he integrated the beams and columns into one single monolithic construction, and this is a very famous illustration of Francois Hennebick's concept of an RCC monolithic frame. In 1896, the first large scale application is what we see. Moving on, Hennebick then, based on this monolithic construction through RCC frame, developed an RCC villa in Bourg-la-Reine and Rhine, and this had a roof garden, it had a minaret, it had solid walls in RCC which were poured in place with permanent precast concrete shuttering. Now, this idea of monolithic construction is being used in a more advanced form today, and it is normally known by the what you'd call the business name or the product name as Maiwan Construction, and here we use these aluminium panels and we erect the entire frame using these aluminium panels, and then and put in reinforcements between them, and then we pour in concrete for a monolithic construction. So that is one way in which buildings are being constructed today. Idea came from Francois Hennebick. Now, with the invention of modern concrete, because of the invention of Portland cement, combining concrete and steel leading to RCC, in Europe it was also called as ferroconcrete, thin, strong, financially viable for long beams, columns, walls, etc. And an architect, Auguste Perret, built an RCC building called the Rue Franklin Apartments in 1902-04, and this plan in a sense predated the work of Le Corbusier's development of a free plan. So what you find here in Rue Franklin, because of RCC frame construction, he is able to provide very thin walls, and it is essentially a free flowing interior between the living room, the dining room and the bedroom, and that is because the entire structure is supported by an RCC frame. Of course, this later on led to the idea or the concept of a free plan by Le Corbusier, and we'll talk about those 5 points of a new architecture that Corbusier had propounded. This is the interior of the Rue Franklin apartment. As you can see how the space is moving freely because of the RCC frame. So the reason why we have free flowing spaces today is because of the technological development of RCC frame or the steel frame. Technology has always played a very important role in developing architecture, and we will see that later is a statement that I often quote: architecture is not driving change, architecture is driven by change. When changes take place in technology, when changes take place in socio-cultural flavors, architecture also starts changing. But there is an added statement by Winston Churchill, who said, first we make our buildings, first we shape our buildings, then our buildings shape us. It is very true that buildings do have a profound, sometimes, not a profound I would say, but a certain impact on people's behavior. A good work interior environment does impact the way people respond to it. But again, I'll point out this: one of the reasons why Industrial Revolution is so important for our study and so important for modern architecture is the technological developments that took place, whether it was steel, glass, cement, and then the invention or the idea of combining steel and cement into RCC were very critical for modern architecture. Sheet glass, for example, one of the first structures to use sheet glass completely in a glass and steel enclosure was the Palm House in Kew Gardens in London. This is the example. And then large permanent enclosures which happened in railway stations also had extensive glazing with these vaults running over the tracks. Because this is a steel frame, these vaults were possible, and because this was a steel frame and because we had glass, we could put it here and allow light to filter in. And this beginning was made in the Lime Street station in Liverpool, 1849 to 1850. Again, I'll repeat, this is a repeat slide. I had shown it in the 18th century slides when I talked about Jean-Nicolas Louis Duran and his earliest proposition that form follows function. He did not say that, but he rather said that the ground plan is the great originator of form. That means first it is the plan, the function leading to the form, and then later on Louis Sullivan said form ever follows function. This is how Jacques-Nicolas Duran thought of how buildings can evolve, that with the ground plan being the great originator, several kinds of elevations are possible over it. Now, we talked about technological changes, we talked about the new materials that came up, we talked about how these materials were implemented in buildings and bridges and how railway tracks and how I-sections came up. But let us look at how society was changing. There were rapid changes in society. It weakened the concept of permanence. Because of social changes, the rise of capitalism, new construction methods, more common for buildings now to become obsolete. The earlier idea that buildings were built to last forever started going away. And now, because of that, because buildings could become obsolete, they could be replaced with newer buildings, land itself became of independent economic value and became a liquid negotiable commodity. It could be bought, it could be sold. It didn't have to remain with the landed classes forever, passed on from one generation to another. Others could buy it, other capitalists could buy it, buildings could be pulled down and new could be built. Now, with these vast changes happening, one of the big things that happened is that if you look at the sequence, factories came up because of steam power, coal was required to run these factories. This coal had to be mined. People were needed in the mines. This coal had to be transported to the factories, so people were needed in the railways, and then there were people needed in the factories to run the factories. When all this happened, the product also had to be sold in the market, so allied jobs came up, banks came up, shopping malls came up. Now because of railways, railway stations came up, corn exchanges, stock exchanges came up, and there was a huge influx of population from village to cities because there was a large demand for workers in the cities now because of these factories. As you can see how population started rising very quickly, and particularly around the time of the Industrial Revolution, and particularly massive urbanization began. But because of this sudden influx and this sudden vast change, terrible housing conditions and slums came up in cities. How do you conceive this massive change? Can you relate to it? Can you imagine it? Yes, you can in a certain way. The same massive change that came physically because of Industrial Revolution is happening digitally today. We are advancing so rapidly in digital technology, in the cyberspace, and there is a very new kinds of jobs, new kinds of requirements that are being felt today. We are also feeling this massive change happening. Though the physical, this was more physical, this was more a physical shift. Today it's more about a digital shift that is happening. Now with this whole influx, there were slums surrounding cities. Medical facilities were required. Housing was required, and new types of buildings were required all the way. Railway stations, warehouses, shopping malls, exhibition buildings. Now the problem was, though there was a great need for architects now, because much more buildings were needed, more different types of buildings were needed, but the architectural confusion, the architectural predicament was there were no examples of building types for them to build on that basis. For example, they did not know what a railway station looked like. They did not know what a modern bank building would look like. They did not know what a modern shopping mall would look like. There was no idea because some of these building typologies just did not exist beforehand. And also, the architectural correctness was no more suitable for contemporary needs. They had documented this very painstakingly. This was using stone, but these stone columns were very different from the new steel columns. They were very thick, steel columns were very slender, and as a result, those classical architecture could not be directly put into the buildings of the 19th century. For example, the temple form, this is the temple that you see here, was very inflexible for the complex functions of a bank, because now it was not just a regular plan, it was a more irregular plan to meet the functional requirements of bank. So this was no more possible. Therefore, the forms and design of classical architecture, documented with so much hard work through the field work they had done, through the measure drawing they had done, had to be abandoned for the sake of the new building programs. Isn't it true today? Many of the things that we had so painstakingly worked for are being cast aside with the rapid digital cyber changes in the new changes that are coming today. On the other hand, as we have seen already the example of John Roebling's Brooklyn Bridge, the civil engineers had no such problem. Why? Because they were not carrying any baggage of past architectural styles. They simply had to put together a technological marvel like these vast bridges. Therefore, engineers gained prominence through the grand use of steel in bridges, in factories, in exhibition buildings. Architects, on the other hand, they did not know how really to treat iron. They knew that iron is vital for the buildings, the modern buildings they are making. But they began by first hiding iron both inside and outside by covering it up, then by exposing it inside as in railway stations, but hiding it outside as you see this outer form of the railway station. And then finally, later on in the 19th century, came up this exposing of iron both inside and outside, and the most famous example is the Crystal Palace, and we will study Crystal Palace separately as a presentation for the amount of learning we get from it. Now, how did they solve this problem? They solved this problem through historicism. They again looked back into history, but they thought, can we use this in more of a principles rather than direct imitation or direct elements being put in. So, they began by a return to Renaissance, by borrowing principles of classical architecture, applying Gothic architecture, and finally a new idea called eclecticism, collection of historic. The word eclectic means a collection of different things. It could be there in art, it could be in fashion. In architecture, it is a collection of different historical architectural styles. So, we will stop here, and in the next presentation I will take you through this architect's approach, and we will see how that got represented or reflected in the new buildings that came up. Thank you.